Hi everyone, welcome back to Operations Research. In this video, we're going to give you and discuss some more about applying linear programming. Okay, basically we will tell you what are some situations that you may formulate linear programs so that its optimal solution provides you some suggestions for your decision making. We will give you some examples and in particular tell you what kind of situations may be dealt with linear programs. Okay, that's my plan today. So I will first talk about one application called materials blending. It's asking you how to decide how to blend the materials to make some products. Okay, and then I will talk about another problem about fairly allocate a certain amount of resources to multiple persons. Okay, and with both of them, we tell you something about linearization. Okay, some formulation may seem to be nonlinear, but when you use some technique, it's possible to make them linear programs. Okay, we're going to summarize that linearization technique at the end of today's lecture. So let's look at material blending first. In some situations, we need to determine not just how many products to produce, but also how many materials to input to the production process. Okay, this happens when we have some flexibility in making the products. Sometimes you see some problems saying that if you want to make one table, you need 6 units of woods and 2 hours of machine hours and so on and so on. Sometimes the materials that you need, the resources you need for making products are given and fixed. But sometimes you have some flexibility in choosing the materials for a product. For example, when you want to make orange juice, okay, you need to blend orange, sugar, water, and many things else to make orange juice. Different ways of blending these materials results in different qualities of juice. Just like if you want a very high quality juice, you may use 100% of orange. Okay, 100% of this product is made by orange. In that case, we can somehow say that the quality is very high, but the cost may be too high for you to do that. So you would ideally blend these 3 kind of materials so that you are balancing between a high quality product and your cost. The goal is to save money while maintaining quality. Okay, we're going to tell you that you may choose to produce some products. Different products have different quality levels. If you want to achieve a certain quality level, you need to blend these materials in a given way. Okay, we're going to give you the details. So let's look at the following example. Suppose I want to blend the materials 1, 2, and 3 to make products 1 and 2. For example, material 1 may be orange, material 2 may be sugar, material 3 may be water, etc. And here, product 1 and product 2 are both orange juice, but with different quality level. We say that the quality of a product depends on the proportions of these 3 materials. And if we want to pass the quality standard for product 1, then we need at least 40% of product 1 is made of material 1, and at least 20% of product 1 is made of material 2. Okay, something like the amount of orange you use for orange juice 1 must be at least 40%. Okay, you cannot use too much water. You need to have a certain amount of orange juice that is made by orange, something like that. And for product 2, you need even more orange. You need at least 50% of material 1. Or sometimes you have some at most constraint. Okay, at most 30% can be material 3. We say that we can sell at most 100 kilogram of product 1 and 150 kilograms of product 2. And that's the maximum amount we may sell. The prices for products 1 and 2 are $10 and $50 per kilogram. Okay, product 2 is can be sold at a higher price, but seems to have a higher quality standard. Costs for materials 1 to 3 are $8, $4, and $3. Okay, so making product 2 somehow allows you to get more money. Okay, by selling product 2, because product 2 is somewhat better. Okay, but product 2 requires a higher percentage of material 1, and the material 1 is much more expensive. So now you face the question about whether to make either product, and in either case, how would you blend your materials? Okay, the amount of a product made, we assume that it is equal to the amount of materials input. So that means if you blend 10 kilograms of material 1, 5 kilograms of material 2, and 5 kilograms of material 3, we say that in total you're going to produce 20 kilograms of your product. Okay, and then you can calculate those percentages. What we want is to maximize the total profit. That's the problem definition. Blend the materials to make products. Now, if we want to formulate this problem, we need to have some decision variables. Our first attempt maybe do the following thing. Okay, I would say, okay, I want to decide how many product 1 and 2 to produce, and I want to know how many materials 1, 2, and 3 should I purchase. Okay, probably this should be purchased, something like that. So I want to know these quantities. However, if we have this set of decision variables, how would you know the quality of each product? It's impossible to do that, right? Because for example, Y1 is the total amount of material 1 you purchase. That's not going to allow you to differentiate those amounts used for product 1 and the amount used for product 2. So we really need to know the amount of material 1 used for product 1 and the amount of material 1 used for product 2, etc. So in general, when you want to formulate a linear program, this always happens. Initially, you create a set of variables. Okay, if you are lucky, then they are useful. You can use them to complete your linear program. That's possible. But also sometimes you first prepare a set of variables, and then you see, okay, they are not enough, or they are not appropriate. In that case, you just need to redefine your decision variables. In this example, let's do this. I know that I need to know the kilogram of material 1 used for product 1, the kilogram of material 1 used for product 2, etc. So in total, I may want to define 6 variables. Okay, and then I call them x1 to x6. Seems to be fine. The definition is correct and precise. However, it is not easy to use, because when you ask what's the amount of material 2 used for product 2, you need to remind yourself that its label is x4. Okay, your name of your variables do not clearly tells you what's the meaning of those variables. When you see x6, it's hard to understand that, to remind yourself that it's material 3 for product 2. So you may want to give your variables reasonable names so that when you are formulating your problem, it's easier to use. Okay? Give your variables reasonable names that allow people to know what they are. And this will be much better. In this case, we have materials, we have products, so it's better to have two indexes instead of just one. Or if you think it in computer programming, it's better to store these values in a two-dimensional array instead of a one-dimensional array. So one thing I may want to do is to rename them as x11, x12, and so on and so on, or just in a compact format. Xij is the kilogram of material I used for product J, I from 1 to 3 and J from 1 to 2. Okay, something I can do so that I can clearly indicate the meanings of these variables. Okay, with that, now we are ready to formulate our objective function to maximize our total profit. The sales revenues depends on the amount of products we sell. Okay, and we know given these quantities, the amount of product 1 I make is x11 plus x21 plus x31 because the final amount for product 1 is just the sum of all the materials you input. Similarly, for product 2 is x12 plus x22 plus x32. Materials have their cost, and that depends on the amount of materials you purchase. And for material 1, we know it's x11 plus x12. For material 2, we know it's x21 plus x22, and so on and so on. So you can formulate your objective function here. Given the amount of product 1 you sell times 10, this is your sales revenue of selling product 1. Okay, this is the sales revenue for selling product 2. This is the procurement cost for buying product material 1, and so on and so on. If you want, you may combine similar terms into the second objective function, but we do not require you to do that. As long as your formulation is correct, then it's okay. Now, we may have quality constraints. At least 40% of product 1 must be made by material 1, which means this, right? The denominator is the amount of product 1 I make, and the numerator is the amount of material 1 used for product 1. So this ratio must be at least 40%. Totally makes sense. It's conceptually correct. However, okay, this is the important part. It is nonlinear. Okay, it is nonlinear. This guy is nonlinear. Why? Because you have a division operation applied on your decision variables. If you want a linear function, all you can do is to add or subtract variables. Okay, you cannot multiply two variables. You cannot divide one variable by another variables, and so on and so on. This is not a linear function. For this nonlinearity, it's easy to solve. We just need to move the denominator to the right hand side, like this. Okay? Then basically we are getting the same thing. Right? We are getting the same thing. And in fact, this is even better. Because in the original case, we probably need to worry about what's going to happen if the denominator is 0. But when we do it in a multiplicative form, like this is much better. So, you may think that these two things are just equivalent, right? But they are just different. This guy is nonlinear. But after you do the modification, this is just a linear function, or a linear constraint. And if your linear program contains something like this is not really a linear program. So you need to make sure that in your linear program, all the functions, all the constraints, all the objective functions are linear. If you want, you may choose other format, like move everything to the left-hand side, or even make them all have integer coefficients, but it's not required. If I am doing this problem, I will just leave my constraint like this. Okay, so go back to the problem. You see that we in total have 4 quality constraints. In the first 3 cases, we require one material to be at least some amount, so it's greater than or equal to. The last one is that it must be at most some amount, so it's less than or equal to. We also have demand constraints. We cannot sell too much. And we have non-negativity constraints, like this. If we combine all of them, we get the complete formulation like this. My objective function to maximize the total profit, subject to 4 quality constraints here. Okay, and demand constraints and the non-negativity constraints. This is how we formulate this problem. Here, before we close this section, I have some remarks. Sometimes you need to redefine your decision variables. You are going to get some more exercises and experiences. Then you know, okay, sometimes I need to do that. From time to time, we may want to use multi-dimensional variables, just like here, x1, 1, x1, 2, x2, 1. This is much better than x1, x2, x3, blah, blah, blah. And even better than A, B, C, D, E, F. Okay? Your variables can be structured in a more reasonable way. Finally, at the beginning, you may formulate a conceptually correct program, which is unfortunately nonlinear. Okay, for some problems you may do this. You have some nonlinear formulation at the beginning. Then you try to see whether you can linearize that nonlinear constraints or objective functions. Okay, you need to do that if you want to use linear programs to solve your problem. Today, we only know linear program, and we only know how to solve linear programs. So if you want to use, for example, the simplex method to solve your problem, you need to make sure that everything is linear. We're going to see some more examples. Thank you.